5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
In-space manufacturing is what we're talking about in this episode. And we have a really cool and qualified guest. Jessica Frick is from Stanford's XLab, the Extreme Environment Microsystems Lab. They recently held a workshop on semiconductor manufacturing and microgravity, just published a white paper about it, and are now even setting up an institute focused on manufacturing advanced materials in microgravity. Enjoy.
My name is Raphael Rodkin, and I'm an investor and advisor to space companies. Just as a reminder, this podcast is for informational purposes only, and nothing should be taken as investment advice. This podcast is sponsored by Nano Avionics, a satellite manufacturer and mission integrator. Their technologies enable many space companies worldwide to offer services that improve life right here on Earth, such as providing global connectivity, conducting Earth observation, or contributing to scientific discoveries. Check them out, and also check out my episode with the CEO and co-founder. Sadly, I am not a rocket scientist, but I'm an alumnus of the International Space University. ISU offers a number of educational programs about space worldwide. Check them out at isunet.edu.
And just some final things before we start the episode about ourselves. If you enjoy the podcast, please leave us a 5-star rating on your favorite podcast platforms such as Apple or Spotify. If you want us help expand our work, you can do so and support us at www.patreon.com/Space Business Podcast, and we'll also put that link in the episode notes. And lastly, you can follow us on Twitter at podcast_space.
Hey, space enthusiasts, welcome back to another episode of the Space Business Podcast. And as you longtime listeners know, even though we're called the Space Business Podcast, and very often we interview space executives and space entrepreneurs, not every episode is like that. Some other times we just have interesting people from the space sector in general who are working on very interesting things. And I really believe today is such an example. And our guest is Jessica Frick from Stanford. Welcome, Jessica.
Thank you so much for having me.
Oh, it's a pleasure. So, Jessica, why don't we start off basically with a quick intro of yourself and what you're up to?
Yeah, so I will actually introduce kind of the background of XLab first, then go into my professional background. So I am a research engineer in the XLab at Stanford University, which is led by Professor Debbie Sineski. And in the XLab, we work on creating and improving electronic devices that are used in environments that are very extreme and harsh. And so what I mean by that is electronic devices that need to operate in environments like downhole environments in the oil industry that is very high temperature, very corrosive. And then other environments such as Venus, where there's a corrosive high temperature environment, but then there's also radiation involved. And so we're really working on improving those electronic devices to operate and sense in those environments. And so what we do at XLab is we dissect an electronic device layer by layer, and we look at it and we say, okay, how can we improve this part of a device, which is very complicated, and make it perform better? And so there are 3 different parts of an electronic device, mainly. It is the first part, which is kind of the active material. So what is physically interacting with what you want to sense? So for example, a gas sensor, there is a material that actually captures the gas and physically interacts with it and then can communicate to the second part of that device, which are the electric circuits. So those are the resistors, transistors, capacitors in the circuit. And then below that, you have the final layer, which is where semiconductor chips get their name, which is the actual semiconductor material. And that's where my expertise is from.
Understood. And so how did you choose to work at a lab that works on electronic devices in extreme environments? Is there any sort of interesting origin or motivation story?
Yeah, actually, so that goes into my background. So I am probably one of the rare cases in the space community where I didn't start in space. I didn't get involved in the space community until 2018, towards towards the end of my PhD because my formal training is in chemistry and material science. So that's what I did my PhD in. And before then, I was just, all terrestrial based applications, growing crystals and doing solid state synthesis to do applications like photoelectrochemistry, so taking water and splitting it into hydrogen and oxygen, carbon dioxide reduction to products like alcohols. And so when I was in grad school, one of the tools a chemist uses is just manipulating variables in their synthetic environment. And so when you are trying to go after a certain type of material, what you do is you just start changing knobs. So you change temperature, you increase, decrease, you change the rate at which you ramp, you cool, you quench. Other parameters are reaction time. That's a tricky part. You need to know how long it needs to essentially cook. Other variables include pressure, concentration of starting materials. All of these are factors that go into manipulating the outcome of your material synthesis. And until recently, the only tools in the material science toolbox are, again, temperature, pressure, volume, etc. But now we can think of using gravity as one of those variables that we can manipulate. And I think that is really exciting. And I kind of came to that conclusion in a roundabout way, again, being completely outside of the space industry to start with. I was growing a crystal and I was like, what is going on here? I'm not getting the properties that I want. I'm getting all of this kind of defect, segregation and then congregation in parts that I don't want. And really, when you look at, the underlying physical equations of crystal growth for these materials, you'll see that gravity plays quite a substantial role. And gravity, G, the constant, is in a lot of these equations. And so I had come to the conclusion, I was like, well, I just need to get rid of gravity. Like, this is it. This will allow me to get rid of the detrimental effects I'm seeing and get kind of the pure structure that I want. And then that's really how I was like, how do I do this? How do I get rid of gravity? And then it was through some friends that I realized that there were actually experiments going on the ISS. And so that's where it started. I was like, oh, that is awesome. There's a brand new tool in material science, a brand new branch, really, because every single material synthesis transformation has some sort of physical, going from a liquid to a solid, gas to liquid, gas to solid, some sort of phase transformation. And in those phase transformations, gravity is a huge factor. And we don't even think about it, right? Because gravity is very innate to us as humans. And so really there's a whole new branch of material science that I was like, oh, I want to do this. This is cool. I want to manipulate these variables. And then that's what led me to Professor Sineski's group, XLab at Stanford, because they were not only doing things in space for space, but also doing the same approach of in space for Earth. So using space microgravity as a tool manipulates the synthetic environment of a material, bring it back down, and explore the benefits of the properties that they got.
And so you guys, I take it, relatively recently ran a workshop at Stanford, inviting a lot of people from the semiconductor community. Mm-hmm. And eventually produced a white paper, which from memory is called something like Semiconductor Manufacturing in Low Earth Orbit for terrestrial uses, as you pointed out. And we will post the link to that white paper in the episode notes. But so let's talk a little bit about that. So semiconductor manufacturing in microgravity. So what does the ability to manipulate the gravity variable, what does it improve specifically in semiconductor manufacturing? And actually, let's maybe take a step back, because we are a non-technical podcast and can't assume that everybody here actually knows how semiconductors get manufactured. So if you don't mind, maybe you can give sort of like the dummies primer on semiconductor manufacturing, and then we'll talk about why space and microgravity makes it much better.
Yeah, absolutely. No, this is a really important point, because I think that the word semiconductor and semiconductor manufacturing are kind of thrown around. And, I'm I'm guilty of this too. It's kind of used as a catch-all, but the supply chain for semiconductor manufacturing is massive. It's on the global scale. So for simplicity's sake, if we start with an iPhone, so to get an iPhone, it's actually a huge global undertaking. So the very first step of creating an iPhone is actually material synthesis. It's growing silicon crystal boules. And silicon crystal boules are massive. They are the size of a LeBron James, very long. Also, the width can be anywhere between, this size of a CD-ROM, if your audience knows what that is, and a vinyl disc.
I was actually going to, for our non-American listeners, just going to comment on LeBron James as a basketball player. So he's very, very tall.
Yes. Thank you for that. So they're very tall basketball players. Okay. And so then these boules get sliced into wafers, and the wafers get taken to facilities like Intel, Samsung, Infineon, where they're taken through the fab process and they are diced into chips. So a circular wafer gets diced into, a 10 by 10 millimeter grid. And those are the small little chips that you see. And so for the Chips and Science Act, for example, that's I'm sure your US listeners are aware of, that's what they mean by chip. So that's the semiconductor chip. And that gets packaged into individual devices and then assembled into your iPhone. And so all of us right now are carrying around crystals. So it's really interesting to think about. Any sort of smart technology that we're dealing with, any sort of communications, really, there is semiconductors at the heart of the device. Without the semiconductors, you can't have iPhones, laptops, etc., as we know it. So again, like I said, the very first step, which I think most people in their minds, they just don't think about this because we've had silicon crystal growth down since, the 1950s. I think the first growth of silicon crystal boules was by the Czochralski method in 1956. And so what people think about when you say manufacturing is kind of the fab labs, kind of the bunny suits in the clean room, that part of semiconductor manufacturing. But again, it really begins with that very fundamental material science aspect. Now, if we think about the semiconductor supply chain, so there is on one end, the assembly part, which gets you your iPhone, putting all these individual semiconductor chips together. And then there's the middle part, which is, again, the fab. So what people are most familiar with. And that's where you're, again, dicing and putting down circuits and whatnot. And then the first part, which is the crystal growth. So assembly in space to make the iPhone, doesn't really make sense to gain a scientific benefit.
Okay, so thanks, Jessica. So for the sort of the primer so far, just I guess a couple of things here. In no particular order. So one, you mentioned sort of the iPhone, but I mean, our listeners probably know this, but just to sort of, really make the point. I mean, semiconductors are clearly really important to the global economy beyond just iPhones. And probably a lot of people these days, thanks to OpenAI and Sam Altman drama, are also like very familiar with what's going on in AI. And AI models are substantially trained these days on something called GPUs, graphical processor units, and they're also based on silicon semiconductors. Exactly. So this is incredibly important. And then the second point I want to make, just to get it out of the way, is so we're going to talk about space, right? And by virtue of this being the Space Business Podcast, of course, everybody here is super excited about space. And yes, we could produce, these things in space, and then ultimately, like you said, even assemble like iPhones or other devices in space and use them in space. But that's not actually the really interesting part in the near term, right? In the near term, the really interesting part is that we bring this back to Earth, correct? That's
correct. Yes. So I think that, the audience who listens to this podcast, we are all on the same team in wanting a spacefaring civilization. And if we're a spacefaring civilization, we'll have, a self-sustaining, thriving in-space economy. But we don't have an in-space economy yet. And one of the ways in which professionals in this area are thinking about kind of kickstarting or funding this in-space economy is actually leveraging existing terrestrial markets. So the economy we have here on Earth. And so that's what I mean by when I say space for space and space for Earth. And so what we can do is look at, okay, there are some aspects of, yes, we can do things in space for the sake of doing them in space and having them, on demand. And so when we're on our, lunar bases, Mars base, we will have those materials. But for now, we don't have those aspects of an in-space economy. So we need to determine what can we do in space that can benefit the products that we can sell on Earth. So how do we take advantage of those existing terrestrial markets? And semiconductors is one of those products that actually benefit from being produced in space, in microgravity, that outweigh the potential cost of their production in space.
And let's just take a step back and connect this to, what you previously, when you gave us the primer on semiconductor manufacturing, right? Because I guess the fact that we, again, we don't do space for space right now, we don't want to assemble a final device in space to then use on the moon or something. That has then, of course, an impact on which one of the activities that you mentioned we actually conduct in space, right? So you're talking about the wafers, you're talking about the fab, you're talking about the packaging. Like, for example, it would seem to me intuitively like the packaging, like we don't have to do in space, right? It's probably more towards the earlier part of the activities you mentioned, right? That we should migrate.
Yeah, that's exactly right. So yes, connecting that back to the supply chain, it's not, scientifically or practically beneficial to assemble iPhones in space or to do the fabrication aspects of slicing and dicing. There are some studies, I will say, that are bringing, an eye to the actual circuit patterning and using microgravity to benefit that aspect. But that's very minimal. But where the actual scientific benefit lies is in the very first step, the crystal growth of the foundational material that makes these electronic devices work.
Okay, and so this was the growth you described in the LeBron James sized
yes,
container.
Exactly.
Okay, and so taking a step back, why does that work better in space? And I assume that has to do with the microgravity, physical follow-on effects, buoyancy, the sedimentation, and so forth. But why specifically do crystals grow better?
Yes, so that's always the question. And I think that what I first want to do is break down space. So as you alluded to, space is, there's multiple aspects of space. Space is just a toolbox, and there are many different tools in space that we can use. And so there are, the vicinity to solar energy is one example of a tool that space gives us. We can capture solar energy, maybe beam it back down to Earth, right? Another tool is the hyperopic view of Earth to do near Earth observations and to look at weather patterns and such. So another really important tool that space has to offer us is microgravity. And low Earth orbit is the nearest point at which we can reach a microgravity environment outside of the Earth's atmosphere. And so it's microgravity that we really care about.
I'm just going to interject just to sort of not to split hairs here, but because I was going to ask you the question whether we can replicate this on Earth or not, right? So you might as well get this out of the way, right?
Okay, fine. I'll get that out of the way.
Of course, we can simulate very short periods of microgravity.
Yes.
Below the low Earth orbit, right? Like on parabolic flights and in drop towers.
Mm-hmm. No, this is a perfect question because this is something that I get asked all the time, which is, can't you do, parabolic flights or drop shaft experiments or suborbital experiments, or can't you just make a microgravity box in the lab and do your experiments there?
Yeah, or even something like a random positioning machine for that sake, right?
Right. So for certain types of experiments, the time frame of, a few seconds to 20 seconds, which I think parabolic flights affords, to a few minutes, which the suborbital flights afford, that is not something that you can do with semiconductor crystal growth. So these timescales are on the hours to potentially days, depending on the size of the material and the identity of the material. So that is something that we can't do. And then, of course, we cannot have just a microgravity lab on Earth because we are still subject to Earth's gravity. Good?
Okay, understood. Okay, bracket closed. Thank you for this explanation. And I'm sure if there was a way that this could be used on suborbital flights, you would have done it, because it would have been such a nice excuse for you to conduct research and go on a parabolic flight. But I understand we have to go to orbit. And also, just to get that out of the way, because of course, and I was very sloppy talking about space, right? Space is very big. And of course, we have the full spectrum of gravity environments, right? But what do you want? You don't want lunar gravity. You don't want Martian gravity. You want microgravity.
Exactly. And I think that, I have been asked the question before of, well, do you think, lunar gravity would be good for some materials? And that's a good question. I think that, once we're established on the moon and Mars, et cetera, that's something that we can investigate. But for now, we know for a fact that microgravity has the beneficial aspects that we need. And so what do I mean by, these beneficial aspects I keep talking about? So I don't want to bore the audience with a bunch of equations that I could list, but there are underlying chemical equations and fluid mechanic and mass transport equations that you kind of learn when you are an undergrad in these kind of hard science classes as a chemist or material scientist that really tell you how the liquid or gas moves during a solid state synthesis. Because again, I mentioned the fact that really there is an important aspect that's happening when you go from when you go through a phase change. So going through a liquid to solid phase change, gas, solid, gas, liquid, solid. And these underlying governing equations really dictate what the final crystal structure is going to be and what the then properties of a device made out of that material will do. So the performance of a semiconductor device is dependent on what the atomic structure of your underlying semiconductor material is. These underlying equations, instead of listing them, a good way to understand them is through the kind of graphics that are placed in the white paper. So the underlying equations that are governing these transformations reveal themselves in phenomena like buoyancy and sedimentation, thermal convection, hydrostatic pressure, and container interactions. And these phenomena under Earth's gravity are turned on, and under microgravity, they're turned off. So as an example, let's talk about buoyancy and sedimentation, because I think that one is probably the easiest to understand. So buoyancy and sedimentation, if you have a liquid body and you put in heavier objects and lighter objects, the heavier objects will sink to the bottom and the lighter objects will float to the top. And this is when the buoyancy and sedimentation effect is on Earth's gravity. But if we go into microgravity, this effect is turned off. And theoretically, we will get a homogeneous dispersion of the heavy and light particles in this liquid volume. So what that means, again, trying to, in a way, understand how that translates to crystal growth. Let's look at a semiconductor that's used for a photovoltaic cell, for example. So for solar cells, you need a certain amount of impurities, actually, because without those impurities, you are going to have an intrinsic non-conducting semiconductor. And so you are purposefully doping in these different types of atoms. And you can think when you're growing these crystals, so you're in a liquid state and you're going into a solid state, you are putting in these little dopants that you can think of as the heavier objects and the lighter objects we just used in that kind of generic example of buoyancy and sedimentation. And so you get this kind of sedimentation of your dopants that you don't actually want, because then that gives you a inhomogeneous distribution of these dopants when really you want them to spread out evenly. And so that's why, for one example, microgravity is very useful, because if you turn this off, then you get that homogeneous distribution of dopants just like you want.
That was great. And it's sort of like the magical effects of microgravity. And sort of maybe to kind of give a couple of, visible examples to our listeners that you may have even seen some of our listeners on photos. So Jessica, you mentioned like the absence of convection. So some of you may have seen that like a flame in microgravity is basically a sphere, and that's because there's no convection. Another example you may have seen is astronauts playing around with basically huge blobs, like huge drops, like giant drops of water, and which is basically because the water tries to minimize the energy spent on the surface tension. And that doesn't work on Earth because there's gravity, but in space you can have a giant blob of water floating around. So there's like some very cool sort of like cool visible things to do, like the flame and the drop of water, but it has, as Jessica explained, some really important, let's call them industrial applications that these special conditions that we find in microgravity can be used for.
Yeah, so those were great examples of what I like to call the macro scale demonstration of these phenomena. But there are the atomic scale demonstrations that you can't see, but they're very real and have great effects on the final product.
Okay, so in that, by the way, let's open up another bracket, because we're talking here about various materials, and the material science is at the root of this all, right? And we've talked a lot about silicon, because of course the current semiconductor industry is substantially, very, very, very substantially silicon based. But does this not also allow us to basically use other materials that we maybe have not used as much in semiconductor manufacturing on Earth? The fact that we can take advantage of these special conditions?
Yes. So that is one of the main points of the white paper, is the fact that, we have been using silicon as the basis for all of our electronics, but we are hitting a wall. And that's very much known in the semiconductor industry, that we need to move beyond silicon-based materials if we are going to, be a society that uses very high power technologies. And so one, very good example of this is electric vehicles. So electric vehicles, they actually use other non-silicon kind of next generation, we like to call it next generation semiconductor materials, which is silicon carbide, gallium nitride, diamond. All of these materials are materials that have a lot of interest right now in use cases like electric vehicles, but they're very difficult to make on Earth. And some of that is due to the underlying gravitational effects that kind of minimize their ability to grow larger. So for example, again, I'm going to take it back to silicon just because it's a very easy thing that people usually understand. Silicon is grown in a quartz container, and you are limited to the size, the diameter of your silicon crystal by the size of your container. And that's something that is also in an effect for other materials like these next generation semiconductors. They're limited in the size at which they can be grown because of their containers and because of the underlying effects of hydrostatic pressure. And so if we were to take these kind of really difficult materials that's, we can get maybe 2-inch wafers, but we can't get anything greater than that. And we take it into microgravity, and then we have, like a release. Don't have to worry about hydrostatic pressure. We don't have to worry about container interactions. Then we will be able to grow larger crystals of these materials.
And so what is the practical sort of summary relevance of having larger crystals? Like what specifically does it improve?
Yeah. No, great question. Why do you want larger crystals? So how the fabrication process happens on Earth, you take your crystal boule, you slice it into wafers, and then that wafer gets diced into individual chips. So in the production line, it behooves you to have larger surface area of your wafer, because if you have a larger surface area of your wafer, you get more chips. And so that is the benefit to doing a large single crystal of whatever material you want. And also it kind of has to do with fitting into current infrastructure, because a lot of fabs are outfitted to perform with larger wafers. And so if you are giving them wafers that are just an inch or two in diameter, it's going to be a bit trickier for them to transition. And that gets us into a whole other question, which is, industry inertia.
So it sounds like the advantages are, did I hear it correctly, in that the advantages are sort of very much focused on the manufacturing process and maybe making that more efficient, like lowering the cost or increasing the revenue, rather than, so if I take another example for, a material where people have explored in-space manufacturing that I'm sure you're familiar with as well, is the certain type of optical fiber, Z-band, right? And then Z-band, the argument, the way I understand it goes like, well, the microgravity basically leads to fewer impurities, which leads to less signal loss. Is there something like that as well in the semiconductors, or is it mostly focused on the manufacturing process efficiencies?
So it's both. And I will say that, again, there's some caveats here that we can talk about. But right now, there's actually both, which is great. This is exactly where we want to be. We want to be doing space for Earth with a product that has overlap in the manufacturing benefits, but then also benefits in the performance of the device. And so semiconductor crystal growth actually dates back to the 1970s, 1973 with the Skylab mission. And if you go back and look at this history, I think that there are about 160, 170 or so crystal growth experiments specifically for semiconductors that have been done since the 1973 mission. And if you dissect those studies, which I've done personally through for a lot of materials, there are some materials there that grow up to 2 times faster in microgravity. They grow to a diameter that's up to 3.3 times larger. They grow up to 1.5 times longer, and they have 1,000 times fewer defects. And so for me, that makes sense. And I understand that because that's kind of how I talk in the world of semiconductors and crystal growth. Whoa, 1,000 times fewer defects, like, whoa, 3 times larger diameter. But what does that actually mean once we take it along the supply chain and we get to our iPhone, right? So let's start off by looking at product yield first, because I think that that's easier to understand. So when you have fewer defects in your crystal boule and you have a more uniform dopant distribution, that means you can use more of your boule. So remember I was talking about earlier how buoyancy and sedimentation on Earth can have detrimental effects of your carrier concentration. And so what happens because of that, the silicon industry has to cut off some of their yield. So they get a boule that is, X long, and then they have to cut off at least 20% of their boule.
So it's like tailings, it's like waste, basically.
Yes, complete waste, right? And I'm being pretty generous with this. So they cut off minimum 20%, sometimes, and depending on the type of material, if it's not silicon, if it's some like gallium arsenide or something like that, it could be more. So, but because of the uniformity that you get in these dopants, and because of the fewer defects that you get, this leads you to a minimum amount of usable volume of 90%. So you could increase the usable volume at least by 10% minimum. So you're cutting off the top and bottoms, just less of it, because you have about 90%, sometimes even more, of the boule that's exactly the type of atomic structure that you are desiring. Now, let's take that boule, and the same boule that, again, we can use more of this length of, we also know that it can be 2 to 3 times larger in width. So we take our longer boule and we slice it into wafers, and the wafers go from, 1 diameter to 3 times that diameter. So what we're saying is you take the boule, you slice it into wafers. In microgravity, you get more wafers per boule because you have a longer length to work with. And then you get also more chips per wafer because your wafer surface area is larger. So for example, if you go from like a 2-inch wafer to a 3.5-inch, which is about a 200% increase in surface area, you're increasing the amount of chips per wafer to about six to seven times more chips per wafer. So again, you're getting more wafers per boule and more chips per wafer. And if you put into account all of these factors of, again, the increase of uniformity in the dopant distribution, 1,000 times fewer defects, 2 to 3 times increase in crystal size, that gives you a product increase theoretically of over 150%, which is insane. But that is what the result.
So 150%. Just what is that measured? This is the amount of product, or what does the 150% refer to?
Yes, the amount. So again, taking something. So essentially your yield is increasing by each step because it's higher quality, and combined with the fact that it's also bigger, you get these, again, insane increases in product yield.
Okay, no, that's clearly very significant. So let me ask you this question now. So you just mentioned a few minutes ago, like Skylab in 1973, and I forget the number, but so basically hundreds of experiments. And by the way, I always tell our listeners when we talk about in-space manufacturing, there is something, I think it's called the Space Station Research Explorer. It's a publicly accessible website. You can actually find every experiment that has ever been conducted, as long, I guess, as it's not classified or something. And it's very interesting.
I don't know about this Space Station.
Yeah, there's something called the Space Station Explorer. It's another website. You can access the experiments that were conducted on the National Lab.
On the National Lab.
I think it was the National Lab, yeah.
Okay, so that's a good point that you bring up, because even though on the National Lab, which the ISS was constructed and is starting in 1998, there's been over 3,000 experiments on the International Space Station. But in terms of semiconductor work, there's only been, I think, around 7 to 9 studies on the International Space Station of semiconductors that have taken place over the last 20 years. Yeah, actually the bulk of, I think about 75 to 80% of the total semiconductor crystal growth experiments that have been done in space were done before the ISS. So we're talking 70s, 80s, and 90s.
So this is why we're talking about it. You mentioned Skylab and probably like the shuttle, the space shuttle as well.
Yes, exactly. Mm-hmm.
Okay, interesting. So, but the question I want to ask you is basically is the following. So, we've like known this is like this looks interesting. There might be something interesting here for a long time. And why do you think this is coming to the forefront now? Why are you guys doing a workshop on this now and exploring this now? And I'm pretty sure I know the answer, but I just wanted to hear your view as well.
Yeah. So that is something that's first of all, it's baffling that we had access to this information and nothing really came out of it back in, again, the 70s, 80s, and 90s. And you'll see actually that NASA put in several millions of dollars. I think in 1989, they put in almost $13 million to consortia that were going towards material science, semiconductor synthesis in space. And $13 million in 1989 is like, I don't know. Oh, and this is USD I'm talking. It's around 40 million USD today, which is just insane. So there was just so much momentum. But then there were a lot of, I think, political transitions that happened going from the space shuttle era to the ISS that kind of, in this area, the ball was dropped. And again, there's so many reasons for this, but a lot of the focus was put on the ISS, and doing experiments in space like semiconductor manufacturing is very power intensive and actually poses a much higher risk to crewed vehicles. So the astronauts that are living on the ISS, there's not really an escape route for them. And so if we are taking these materials and heating them up to high temperatures, high pressures, even if there is a very slim chance of, something happening, the furnace going off and explosions or whatever inside the ampules, that could pose a huge threat to the health and safety of the astronauts.
To interrupt you, but like from everything I've heard from you about the production process, it also seems like there is really no reason why there should be like manual intervention, right? And sort of, I noticed from some other like types of, production processes proposed in microgravity more on the bio side, right? Where we say like, well, the less astronaut intervention, the better. I mean, you mentioned the health reasons, but also like astronauts are really expensive. Like NASA charges, I think, $130,000 an hour for an astronaut hour.
Mm-hmm. Yeah, no, same thing goes for the materials, advanced materials aspect of in-space work. So less astronauts, the better. But right now, all we have is the ISS and astronauts are there. And again, I don't know really the reason for that other than I think a lot of it is about kind of national pride, I think, for the US, having astronauts in space. And then it's also kind of a global collaboration with many other countries, just seeing, individuals from different countries up there in space together. And I think that is, I don't know, in my opinion, it was definitely one of the reasons why more intensive experiments like semiconductor crystal growth kind of got put on the side burner because it just wasn't important politically at the time.
But so, like you should point out, right now it's basically ISS. I guess for completeness, we should mention there's another space station up there right now, which is the Chinese Tiangong. But obviously, geopolitics are complicated, as everybody will appreciate. And then there's also hypothetically, I guess you could go to SpaceX and say, hey, I want a Crew Dragon as a free flyer, and they'd probably be very happy to sell it to you if you pay enough money. But that's a lot of space. But so if I put on my venture capital hat for a moment, right? So we are actually, as a VC fund, we're invested in several startups which are proposing to put up, let's call them microgravity manufacturing platforms, mostly free flyers. Then there's some, people who want to build private space stations as well, right? Like Orbital Reef and Starlab and so forth, Axiom and so forth. So the really interesting thing right now is that, I actually haven't counted this recently, but it's probably something like 24 startup projects out there which want to put up private platforms in orbit, which can be used for, well, they could be used for tourism, but they could also be used for in-space manufacturing. So my question to you is now, like, if even some of them work out, this seems very interesting because, they can be used for doing something like semiconductor manufacturing steps. What would an ideal platform look like? Like, what do you need? Like, just like basics, like in terms of like size or power requirements, other things.
So you're touching a nerve here because this is a question I get asked all the time. I can't tell you the amount of kind of cold emails I've gotten from companies who just say, oh, I want to pick your brain. Like, what do you need? What's the size? What's the power, et cetera? And I guess I kind of want to answer your question with a question, which is these 24 new companies. What does the composition of that team look like? Are there any actual scientists who do material science, or are they all aerospace engineers?
Oh, let's see now, Jessica, now you're touching one of my nerves, actually. So, okay, let me give you the answer on that. The people who are building platforms are substantially all aerospace engineers. So what I would like to see, and this is purely my own personal opinion, again, wearing my VC hat, is I would like to see a world where there's people who build the platforms, or at least let's call it the outer platforms, so to say, right? But if it comes to like, let's call it for lack of a better word, the payload, right? The actual production facility. I would like to see a separate class of companies, which by and large hasn't emerged yet, to be honest, of people who are actually deep subject matter experts in exactly what they want to produce in microgravity. And so, okay, I'm going to just kind of brief marketing. Some of my listeners may know that one of my other roles is I'm currently acting CEO of a space biotech startup called Prometheus, which is growing human organ tissue in microgravity. And I'm like the only guy who doesn't have a biology PhD on that team. And that's exactly the way it should be.
Oh, that's awesome. Yes.
But that is not the case that is a very rare occurrence at the moment, right? So as a VC, I would like to find, for example, we're talking about semiconductors here, so let's stay with that, right? I don't want to turn this into a bio episode. I would love to find a team, a startup company that's like, hey, we really agree with what Jessica and the XLab at Stanford are saying. We want to focus on producing semiconductors factors in microgravity. And by the way, we have exactly the right background, and we can work with these aerospace guys to kind of, perfect the right kind of platform. But there's really very few examples of that at the moment.
Mm-hmm. Yeah, I think that, again, I'm really appreciating your take on this, because in my mind, I kind of like to use the analogy of, Intel is hiring a construction company to like build their new facilities, but then the construction company is also doing semiconductor fabrication and is selling you semiconductor. It doesn't make any sense.
No, that doesn't surprise me.
So it's but because we've been in this kind of aerospace boys club for so long, for anything that's done in space, that we're just hardwired to, oh, it's in space, that means you have to have an aerospace engineer. Whereas we're really moving to new areas of science, so new areas of material science, microgravity material science, where you need people with, again, that very deep scientific knowledge. And so in order to help these companies, because we do want to help, we want to make the area flourish, because we really care about this deeply. I'm very passionate about making semiconductor manufacturing in space happen. We decided to, that was one of the outcomes actually of the white paper, which is the fact that we don't have an ecosystem. So the fact that these companies have to go to, again, cold calling people, asking for help, and going to, databases that actually don't go back all the way in history to where the real semiconductor work is happening. We need an ecosystem of support for these startup companies, for the academics in this community that want to do work. So people like me who aren't from the space community to begin with, but are like, oh, I see that microgravity is a tool that I can use. How can I do that? How can I partner with these startups? How can I partner with companies that are also in the materials realm? So that's another major part of this, is that there's a disconnect between the space community and then companies that actually could benefit from microgravity as a tool. And so there needs to be a space where we bring in, companies like Applied Materials, companies like Intel, like Samsung, Infineon, et cetera. And we're like, hey, do you guys want to start doing, diamond devices, GaN devices, silicon carbide devices? You want to sell your devices to, Tesla to make electric vehicles? That means you need to start investing and looking into the benefits of this new cool tool that we call microgravity to grow the substrates that you need. And again, there's a disconnect, because as soon as you say space, their eyes kind of glaze over and they say, oh, space, that's too expensive. That's going to really disrupt the supply chain. And it's like, and the semiconductor industry in general already pours in literal billions of dollars every year into across all parts of the manufacturing process. So again, we need to support these companies who are asking, okay, well, what are the specs you need? And so we need to bring them together with the material savvy companies and academics in the field, and we need to work together. And that was really the premise of the workshop, because we saw this disconnect between these two camps. Well, actually three camps, the funders. So VCs and other funding sources like corporate VCs, there's a huge disconnect between the funding, the aerospace community, and then the materials community. And the point of the workshop was to bring in all of those parts and just talk and be like, okay, what do we need to do to make this happen? Because there was so much momentum going into, the year 2000, but then it just completely dropped off. And we are telling you, the scientists are telling you, the benefits of growing these crystals in space are the real deal, the killer app, if you will, of in-space manufacturing for Earth. So how do we make it happen? And it was a lot of fun, the workshop, because there are just so many different opinions. So getting them together was something that we wanted to do. And again, the funding structure for these types of companies and the infrastructure required to do these types of studies is just a huge disconnect. And so what we realized is we need a home for this new community because we can't really be an offshoot of, American Chemical Society, for example, because there's just not enough aerospace space knowledge there. There's tons of chemistry and materials background. We can't really be an offshoot of all of the space communities because, again, you get saturated with the space way of kind of thinking, kind of like a construction of the outer shell, if you will. And so we need something that kind of marries the two. And so that's why coming out of the workshop, the resounding conclusion was that we need an ecosystem, we need a home for this. And so what we're doing is launching an institute. So the Institute for In-Space Manufacturing of Advanced Materials. Because another thing that came out of the workshop is, semiconductors is where we started because there is a huge political push, especially in the US, for shoring up the semiconductor manufacturing aspect. And that's, again, I kind of touched. Yeah, exactly. So it has it's kind of the Goldilocks zone of what you're looking for. You're wanting something that there's a national security need for, which the government recognizes there's a national security need for semiconductors. But then there's also the economic viability. And so semiconductors is perfectly in between. But then if you want to kind of go a bit deeper, what are semiconductors? And semiconductors are a type of advanced material. And by what I mean by advanced material is that these are types of materials that take really extreme environments to make them. So high temperature, high pressure, toxic chemicals, they all are the same. So in my graduate work, for example, I not only grew semiconductor crystals, but I also did solid state synthesis of alloys, high entropy alloys, and superconductors. And all of these types of advanced materials take the same infrastructure. And so if we figure it out for semiconductors, we can then just take that and translate it to, let's grow some superconductors, let's grow some topological insulators, and let's really get this quantum computing happening. So people, I think, really need to make those connections of, okay, if we figure out how to do these kind of extreme transformations, the limits are boundless. So really that is what we're after. And so instead of just focusing on semiconductors, the Institute, again, is for in-space manufacturing of advanced materials because, again, all of these really important materials in our infrastructure, in our everyday lives, relies on these very extreme cases. So that's what we're launching, an institute, so we can put together, again, market report are an example outcome of this, because I know you had someone from McKinsey come on. So that McKinsey report, where it was reporting on different sectors of beauty, healthcare, pharma, semiconductor industry, they were really focusing, I think, on the fabrication aspect. So, we're going to be putting fabs in Leo and doing fabrication there. And that's actually not where, again, the scientific benefits are. You need to look deeper into the, again, fundamental crystal growth aspect to really piece apart where the value creation is coming from. So the value creation in semiconductors, again, is in the crystal growth. And what the Institute will do is dissect it piece by piece and kind of be a dot connector, because I think that this area is super large and complicated. And so we need to say, okay, let's look at cadmium telluride, for example. Cadmium telluride has been grown, around 10 times in microgravity. All of the studies reach the same conclusions that with cadmium telluride, you can get all of these benefits. Okay, if we take those benefits and we extrapolate them to their to wafers and into their devices and into the assembled product, what does that mean? What are we getting? Like, what is the percentage increase in efficiency? What is the, if it's an electric vehicle or a solar cell, how much more energy are we extracting from the sun? Or how much further can you drive in your electric vehicle because you have a much higher quality crystal from space? And right now we don't know. And I think that that's the biggest question that investors are always asking. Well, what's the value creation? And the biggest pain point, I'm sorry, I'm like going all over the place because I have just so much to say. But what the investors want to know, where's the value creation? And again, we can speculate and we can extrapolate based off these studies that were done mostly in the 70s, 80s, and 90s. However, what happened with the community in this time is that the people doing these experiments were researchers with my background, right? Crystal growth. And so they would go grow their crystal, analyze the really cool benefits of it, and that's it. There has been only 1 or 2 studies that have actually taken a crystal grown in space, sliced it into a wafer, done circuitry, diced it, and then did the device characterization. And so what we need as an industry is to show the corporations, large semiconductor corporations and funders, really, that the benefits we see from the crystals tracks all the way through the supply chain. And to do that, we need the infrastructure, and we don't have the infrastructure. We cannot grow things. Let me tell you this. We had better capabilities in the 70s, 80s, and 90s than we do today in space for these types of materials. We cannot replicate, the gallium arsenide studies that were done in the 90s. We can't grow silicon.
There's only like one furnace on the ISS, right? Which is like sort of maybe usable, maybe not. I don't know, from memory.
Yeah, so the ISS is limited because even though the hardware on there is capable of, let's say, going up to 1400 degrees Celsius, which is something that you need for some of these materials, you can't go up to those high temperatures because there are safety limitations. And even if you were to go up to those high temperatures, you have to deal with all of the vibrations occurring on the space station because the ISS is a mixed use lab space. And that's just not how labs operate or manufacturing facilities operate on Earth. You don't have, your exercise bike right next to your crystal growth facility.
Yeah, which is literally the case on the ISS. And this is why we need the specialized, the new platforms, like you said. But the institute you're saying, it sounds so interesting. And actually, look, Jessica, so many, I think all of the things you said, sort of people having prejudices about space being too expensive, the disconnect between industry, community, and space, this is all exactly the same things I'm seeing on the bio side. So I'm actually really excited that you guys are starting an institute. So let me ask you, maybe as we kind of come towards the close here, a couple of questions on the institute. It's like, one, what do you see as sort of like the main activities the institute will do? And I think you already mentioned like one could be writing reports and probably white papers. And then the second question is, if somebody's listening to this and they're like, oh, this is really exciting, like how can they get involved?
Got it. Okay. Yes. Thank you for putting me back on track because I will talk for literal hours. So the institute, there are a few main products. So like I mentioned, market reports is one of them. And we would love to partner with McKinsey and do, an in-depth study on semiconductors in space. And that's something that is super important to us because that's how we're going to convince the skeptics in the world that, look, there's the value right there. Another important aspect of the Institute is to put together recommendation reports. So like we were asking earlier, what are, what's the power, what's the size, et cetera, that you need. And in the recommendation reports, we will be putting together specific reports. So we're going to say, okay, based off of our team of experts that we have as part of the Institute, we know that, if we take into consideration the value creation, we want to go after semiconductor XYZ. And to do semiconductor XYZ, it requires this amount of power, this amount of time in microgravity. It requires these toxic chemicals. It gives a layout of and we want to create kind of a database of this. Okay, if you want to go after, this material, use these parameters, those materials use those parameters, et cetera. But overall, we should be able to, again, kind of come up with a system that, you don't have to use necessarily a new facility for each type of material, but you can tweak the design a little bit to make it more kind of bespoke to your particular material goal. And so that's what I think is a super important aspect of the recommendation report. And it's also kind of another aspect of the Institute is kind of guiding the industry. So again, I stated the fact that we started with semiconductors because of that overlap of political and economic viability. But where do we want to go next? Is it semiconductors? What semiconductors? So, or do we want to go to superconductors? Do we want to make, diamond crystals that we can use for quantum communications? Do we want to go to high entropy alloys to create really strong structures? Which ones is it? And how do those kind of overlap the benefits to, society overlap with the market viability? And so where is that overlap? And that's what the Institute is doing. And so we're also putting together a database of all of the kind of advanced material aspects, which was actually started by Professor Ann Wilson at Butler University. And that's been a huge important aspect of this field, is really just getting together all of the studies that were done pre-ISS and understanding, okay, there's some lost knowledge here. We need to go back and look at that. And then, of course, just a community bringing together. We will offer conferences, and that's just, again, a point of bringing in the getting face time with materials companies, semiconductor corporations, bring them in, be like, so space it's not scary. Come in, like, welcome. We're nice, and it's a way to, actually, the part I'm most excited about, honestly, is this series of webinars that we're creating. So the webinar series is geared towards education, but not K through 12 education. It's really geared towards people in the decision-making roles at companies. So people like executives in the C-suite, top-down approach, because we need to make them understand that microgravity is a tool. So just like you can purchase a new robot from for your factory, you can kind of purchase a tool like microgravity to use in your product line. And so that is where, we'll be answering questions. I think the first episode is going to be Microgravity 101, where we kind of go over what we just did about what is microgravity, why can't you do it on Earth, etc. So I'm really excited about that series, because that is, I think, never mind, the technical problems that we're going to be faced by doing this in space and the scientific difficulties. But the biggest thing in my mind is that inertia of really changing people's mindsets about doing things in space, moving their supply chain moving part of their supply chain rather to low Earth orbit.
I fully agree with you. I always say that sort of in my mind, the education part is so important. The education part between these various communities that you mentioned, sort of certainly the space community and sort of the industry. And again, I'm seeing the same thing on the bio side with the pharma companies, right? And then also the investors that you mentioned. I think education is very important. And if you're doing something like webinars, if you guys, I don't know, you could even do like an EDX course with Stanford or something, like anything you do at education side.
Yeah, that's fantastic. A great idea.
And I'm actually in parallel, I'm thinking about a lot of the same things on the bio side, and we can certainly compare notes. So, how can people get involved? So they hear this and they think this is great. By the way, does the Institute have a name yet, or?
Yes. Yeah. So it's called ISMAM. So the Institute for In-Space Manufacturing of Advanced Materials. It's very, on the nose, but it is exactly what the title states, again, is advanced materials in space manufacturing. So that's what it is. And we have a website that I can give you the link in the show notes. Yep. So we have a beta site where you can join our mailing list and learn more, because we are trying to kickstart the funding for this institute, because I think, again, it's super important to have this type of ecosystem and home for these new startups that are popping up. So I think that just like those startups need funding, this institute also needs funding. So we're really looking to help with the funding, and this is a nonprofit, by the way. So donations for nonprofits, that might be something your audience is interested in. But also getting involved, we're filling out our advisor board. We have a lot of really great folks in the, again, semiconductor world. So for example, we have Dr. Todd Youngkin, who is the president and CEO of the Semiconductor Research Corporation, who is on our advisor board. We also have Dr. John Chen, who is the technology leader for the Silfex company, which is a subsidiary of Lam Research. So we are looking again for strategic advisors to help us out with that. Also, we need help with putting together like an interface. Honestly, just people who know how to like make websites. And I know that there are, a lot of AI programs now where you can just, it just makes your website for you. But we just need someone to help us with that.
Okay, so lots of ways to get involved. This is great. So we post the link to the in the show notes, and people can contact you there. And it's a great initiative. So Jessica, as we sort of wind down here, final question is always the same, irrespective of episode. It's going to be the same for you as well. Do you like science fiction? And if yes, what are some of your favorite science fiction works?
Yes, so I do, but with one caveat, which is that the science fiction has to be set into the future, at least like 100, maybe 1,000 years. If it's too near future, I get stressed out.
Right.
Because it's like, oh, wow, I'm really anxious. I need to, I'm part of making this actually happen. And it's like more like work to me than actual enjoyment. So I like things that are set in the far future.
Okay, I hear you. Like, and we already survived 1984, fortunately. So
yeah. So the a book series that I really love is by a UK author, Adrian Tchaikovsky, Children of Time. So it's a trilogy: Children of Time, Children of Ruin, and Children of Memory. And those three books are phenomenal because the premise is kind of fun. It's kind of a spider civilization that is evolving to be spacefaring, is one aspect of the first book. And I really like it because it gives you, it's not totally alien. So we're kind of aware of what spiders are and how they build their webs and etc. But it gives you a different perspective of what a spacefaring civilization could be from kind of something that's familiar, but a little alien too, so that we can understand it. And so what I mean by this is humans, we're kind of set in our ways and we want to build these very rigid structures. And so that's kind of like what we see, very angular, rigid stations and ships and whatnot. But the spiders in this book, their spacefaring civilization has more kind of flexible types of structures, and that can be manipulated much more easily in a 3D environment. So that's what I like.
This is great. I don't think anybody has mentioned this before, so this is a good new one. So thank you very much for that. And now that I'm obviously a huge science fiction nerd, which is why I always ask this as the last question. And now that I think about this is actually a huge gap in science fiction, at least as far as I remember. There is no work I can think of immediately where there is like, large scale microgravity manufacturing. And that just seems wrong. It seems like a gap.
Yeah, no, for sure. It's interesting. There is a show, I think, on Apple TV, For All Mankind. I can't watch that show because it gives me too much anxiety because there's a lot of, near future stuff, right? And in passing, I think it was I have a friend who watches it, and also my husband watches that. And he told me that in season 2, episode 1, in passing, there was some character who was like, oh, we need those reports on the silicon boule manufacturing in Leo or something like that. And I was like, oh my gosh, that's way too close to home. So there is some aspects of manufacturing seeping into sci-fi, but yeah.
Gotcha. Jessica, thanks so much for coming on, for explaining semiconductor manufacturing to us, how microgravity could improve it, and your initiative of your group with the Institute, and good luck with that. And again, we'll post it in the show notes, and maybe we'll talk again in a couple of years and see where it went. But thanks so much for being here.
Yeah, thank you for having me.
Well, that's it for another nominal episode of the Space Business Podcast. If you like this podcast, please consider giving it a 5-star rating on your favorite podcast platform, such as iTunes. You can follow us on Twitter at podcast_space. Also consider supporting us at www.patreon.com/spacebusinesspodcast. If the podcast got you interested in learning more about the business opportunities in the space economy, check out my new online course on space entrepreneurship on udemy.com. The link is in the episode description. Lastly, if you have any feedback, including ideas for guests, and that may include yourself if you have an exciting space story to tell, or interested in being a sponsor, drop us an email at spacebusinesspodcast@gmail.com. I look forward to seeing you for the next episode.